Today I will talk about a message authentication code, the BRF, based on Ascon. This is a joint work with Christoph Zebraunik, Maria Eichelseder, and Martin Schleffer. So before talking about Ascon MAC and BRF, let me start with a short motivation. So today we have around 50 billion devices in the IoT worldwide, and this number is exactly expected to double by 2030. And we see a number of increasing devices connected to the IoT. While this offers many advantages regarding opportunities and many use cases and ease our daily life, it's a serious challenge for security. In particular, every connected device to your network actually offers also a doorway for an attacker. And there is an urgent need to protect data transmitted or generated by the Internet of Things. However, in practice, implementing security on these constrained devices, if you think about this high number of low-end sensors with limited computational power and having rigorous energy consumption problems, if you think about these battery-powered devices in general, implementing strong security is considered very difficult there. In particular, when you keep in mind that current standards, like for instance ASGCM or SHA-3, are particularly designed for high-end servers and not taking into account those use cases. And this was also recognized by NIST, National Institute of Standards and Technology in the US, where they basically run a kind of public competition over the last 5 years to identify so-called lightweight encryption schemes that offer both confidentiality and authenticity as well as hashing for those particular use cases, which are more efficient than current standards like ASGCM or SHA-2. And these competitions in symmetric cryptography are very common. So past competitions like the AES competition or the SHA-3 competition led to standards like the AES or SHA-3, or currently there's also a competition ongoing for post-quantum cryptography, where the goal is to find some quantum-safe algorithms to replace RSA and ECC in the future. And in these competitions, typically, people from academia and industry submit their candidates to NIST, and then they'll evaluate it in a public process by industry and academia to identify the best algorithms to be standardized in the future. And Ascon was one of those algorithms, which was then selected beginning of last year to be standardized by NIST. So you may wonder, why should you use Ascon? We have already AES and SHA-2 in place, and it's already standardized by NIST. And first of all, typically lightweight cryptography is still basically considered to offer less security than AES and SHA-2 based on algorithms like present, height, and all those schemes are standardized by ISO. But in fact, all these candidates submitted to NIST as well as Ascon provide a comparable security margin and security level as AES-128 and SHA-256, which means it can be used as a drop-in replacement of existing standardized algorithms. And the main reason why you want to consider to use those schemes in your applications in the IoT is, of course, efficiency on low-end microcontrollers, both in software implementations and hardware implementation. So public benchmarking in the course of the NIST competition basically showed that if you look at software implementation on these low-end microcontrollers, you get 3 to 5 times higher speed than implementing ASGCM. And if you look at hardware implementation, what you typically get is twice the throughput with half of the energy, which is again very interesting if you think about all these battery-powered devices. And last but not least, typically in applications where some adversary might have access to your device, you also want to protect your implementation against so-called side-channel attacks, where one is tampering with the implementation or measuring power consumption, stuff like that, trying to extract the key. And this is also something you can do very efficiently for Ascon, which is to be considered to be hard for AES. So in summary, basically Ascon allows you to secure data in the IoT, where this was considered very costly before, which you can do now more efficiently. So how does Ascon work like? So I mentioned before, in this NIST competition, they were looking for an authenticated encryption scheme and a hash function. So the authenticated encryption scheme Ascon is actually quite old. It was designed more than 10 years ago. as a response to another cryptographic competition, not the NISQ competition, but the CISA competition, where academia was searching for new authenticating encryption algorithms which offer significantly advantages over AES GCM. And already there, Ascon was selected in one of the categories, namely for lightweight application as the winner. And then for the NISQ competition, we added a hash function, which you can easily do due to the nice structure of Ascon, which is based on a response construction I will explain in a minute. And then last but not least, very recently, so in 2001, we also added a message authentication code in the PRF, which I will present today. But before having a look at the message authentication code, how does Ascon look like? So as I mentioned before, it's based on the sponge construction. So it's a permutation-based design, and the core of the algorithm itself is a 320-bit permutation, which is a rather small permutation compared, for instance, to SHA-3, which can be efficiently implemented on those constrained devices due to the small state size, because this basically then results in good performance on low-end microcontrollers and very efficient small-scale hardware implementations as well. It's based on the sponge construction used in different modes to either get an authenticating encryption mode and hashing, or an mechanic PRF very efficiently. The only difference to the classical sponge construction is that in Ascon we use a key initialization finalization AAD scheme, which I will explain in a minute, which offers many advantages. In particular, if you think about side channel attacks, so you can do different trade-offs in the implementation to be more efficient there. So how does the design look like? As I said, the core is this 320-bit permutation, which is basically arranged in a state of 5 64-bit registers, and then you just apply an S-box to the columns, 64 times the same S-box, which you see here on the button, which is an affine equivalent to the Catch S-box used in SHA-3, which is very efficiently to implement both in software and hardware, having only a few additional XORs. And then in a linear operation, to get a high diffusion there, we basically apply a few XOR and rotations on each of these 64-bit registers, which is again motivated by the sigma functions of SHA-2. And putting that together, we get very nice cryptographic properties, and obviously that's very efficient to implement both in software and hardware due to the simple structure and the few number of operations. And in particular, what you have to note here is that the algebraic degree of the S-box is only 2, having a few AND gates, which makes it very efficiently to implement if you consider sectional attacks and stuff like that. So as I said before, the permutation has very nice properties. In fact, we can even prove good diffusion against and security against common cryptanalytic attacks like linear and differential cryptanalysis based on the properties of the permutation. It's very simple to implement, as you have seen before. It's both efficient in both software and hardware and offers very flexible trade-offs for implementing that. And as I said before, it's efficiently to protect against sectional attacks. So how to use that now to build an authenticated encryption scheme? That's rather easy, what you see here on the slide picture. So in the authenticated encryption scheme, you take as input a key and a nonce, a number unused once, maybe some data you want to authenticate but not to encrypt, and then the data you want to encrypt. And the output should be the encrypted data, and of course some tag, which you can use to verify the integrity of that. So basically you start here in the beginning with the key and the nonce, and some predefined initial value. You put that in the 320-bit state, and then you apply this round function you have seen before 12 times. And then you XOR the key again. And then you process the associated data, which you see here. Once you're done, you stop. Here you only apply this permutation 6 times, and then you start encrypting the data by XORing the plain text and taking the ciphertext as output. And once you're done at the end, you basically do the same as in initialization. You XOR the key again, apply 12 rounds of this permutation here, and then you apply the key again, and then you extract the tag of 128 bits. So it's actually very simple to implement, and the cost is mainly determined by the state of this permutation, which is only 320 bits. So how do you do decryption? That's very nice. It's basically almost the same as before. You just only swap here plaintext and ciphertext, which means you can implement decryption and encryption with almost no implementation overhead. So for Ascon, we have 2 versions. The version I've shown you before is the version with 128, 12 and 6 rounds. There's another version which is a different trade-off between number of rounds and the block size of processing the iteration. And there is a difference in performance. So the 128 is slightly more performant, but The original version provides higher robustness against implementation trade-offs to be secure against satchel attacks and stuff like that, if you consider that the internal state while processing data might be compromised by some software attack or some satchel attack. There you can still show, it's a nice security proof, that even in those very strong attack settings, you still achieve 128-bit security, which is very nice. While for the A version, it's only 96 bits, which is still sufficient considering practical attacks. So what about the hash function? Hash function is working very similar as you have seen before. Now we always use 12 rounds of this permutation, and that's the classic exponential construction we use from SHA-3. You start with a predefined initial value, you absorb a message of blocks of 64 bits, and when you're done, you start extracting the hash value. So if you want a 256-bit hash value equivalent to SHA-256, you do that 4 times. But of course, we also define an external output function, like it's the case for SHA-3, called shake256, where you can produce arbitrary length output very efficiently. And obviously, implementation override of the hash function, if you already have the AAD scheme in place, is very small. So what about message authentication? So in practice, now you have something where you can do authenticate encryption, so encryption and authenticity, and you have a hash function. But in practice, often you also want a message authentication code or a BRF for doing key derivation or stuff like that, or encryption only. Of course, you can always build an encryption scheme based on a hash function, but this is not so efficient in practice. And we see, and we got the feedback from the cryptographic community in industry, that there's actually a need of an efficient BRF and a MAC in practice. And since the nice structure of ASCON, it's actually rather easy to add, as you will see in a minute. And as I said, you can do it on a hash function, but this is typically less efficient. So how does ASCON, BRF, and MAC look like? So it's again very similar to the hash function, always using 12 rounds of the permutation. The main difference now is that you have here now some key in the beginning, and if you look at the BRF and the MAC, and not an hash function anymore, this allows you to increase the number of bits you absorb here and the number of bits you squeeze by generating the DAC. So instead of only absorbing 64 bits, as you have to do for the hash, otherwise it's not achieving the sufficient security level. If you use now here a key in the beginning, you can absorb 256 bits. And you can squeeze for the DAC chunks of 128 bits. So obviously, this is much more efficient than using the hash function in a KMAC-like mode for building a message authentication code or a BRF. In fact, it's about 4 times more efficient because you can process 4 times the block size in the absorbing phase for the MAC. In addition, while this is very nice for doing message authentication codes for long messages, there might be some applications very interesting that actually have very short messages, like low-cost mutual authentication, where you do some challenge response protocol with a small nonce. Or if you want to do point authentication and applications like that. And for this case, we also defined a short BRF, which is more or less based on the initialization of ASCON. So if you remember the picture before, in the beginning, we had the nonce and the key. We do 12 rounds of the permutation, and we XOR the key again. And we basically take this construction to build a short BRF, having an input, which goes at the place of the nonce of at most 128 bits, and then you produce an output of 128 bits for the DAC. And obviously, this is very efficient to implement and have many nice applications in practice. So what about security? So there is a formal security proof for both the BRF, the MAC, and the short BRF, which shows that assuming that this permutation as usual is an ideal permutation, you can show that this construction is secure, achieving the desired security level of 128 bits. And there was a nice security proof by Bart Menick in 2022, which basically shows that exactly for our construction. And of course, we rely in the BRF and the MAC heavily on the previous cryptanalysis done by us, which was actually presented also to TRSA in 2015 already, and many others for the security of the construction. And basically, best known attacks on ASCON AAD scheme basically can be transferred and translated for the message authentication code and the BRF. And what you see, the best known attacks regarding key recovery are for up to 7 out of 12 rounds of the permutation. So there is a quite good security margin of 5 rounds, and the complexity is very close to a brute force attack. Also regarding forgery, so basically attacking the finalization, best attack is for 3 out of 12 rounds based on differential cryptanalysis. So what you see here, actually there is a huge security margin for Ascon, also including the MEC construction. Yeah, here are some related work. You can have a look what people did on Ascon. Also for the permutation itself. So what people typically do is to get some confidence in the security of the design, they also look at the building blocks. And as I said, the security is based on this permutation. And there was a lot of work done on the Ascon permutation in the past. And although we do not require ideal properties of the permutation to get a secure scheme in practice, it gives you some confidence in the design of the scheme. So most of all, for the S-box, as I said, again, has very nice properties. It has algebraic degree 2, which you need, of course. It's the lowest you can do. We do that for being efficient to implement protect against side channel attacks. But we added this affine layer to the Keccak permutation. And the main motivation for that was to get good properties that allow us to prove security against differential and linear cryptanalysis, which are one of the main common techniques for attacking symmetric ciphers. And also for the linear layer, we chose it in a way that it's efficient to implement as well as to achieve good properties when putting together the S-box and the linear permutation. Again, a lot of work has been done on permutation. I think that's the most interesting one. That's basically showing the security level of the permutation against linear and differential cryptanalysis. There was a nice paper by a colleague of ours from Radboud University, which basically could show that the best differential and linear attacks already have a probability below 2 to the minus 129, or even more that for linear cryptanalysis for already 6 rounds of the permutation, which means if you consider this attack vector, you can at most attack 5 rounds of the scheme, while we use 12 rounds, for instance, in the Ascon MEC construction. And that's a very nice paper because it gives high confidence in the security of Ascon against those attacks. And all the other attacks I've shown you before for 7 and 8 rounds, for 6 and 7 rounds, they are based on algebraic attacks, exploiting the low degree of the S-box. But also there you could show that due to the structure of the S-box, you get a low degree, and achieving more than 7 rounds seems very hard at the moment. And again, we have still 5 rounds of security margin here. So I think this was my last slide regarding security, so let me summarize. So security level of Ascon is 128 bits, which is comparable to AES at 128 and SHA-256. In the last 10 years, it has been thoroughly analyzed by the cryptographic community. There have been many papers published on the security of Ascon in the past, showing that it provides a quite good security margin against well-known techniques in cryptanalysis. It's very efficient to implement on constrained devices, both software and hardware. I don't put all the benchmarking numbers from the NIST competition here, but you can have a look. All of them are online, basically confirming what I said, typically twice as fast in hardware and around 3 to 5 times faster in software implementations. It allows very efficient side channel protection. Also, there are some public implementations available if you're interested. And although it was designed for these constrained devices, as it's defined on 64-bit words, it's also very efficient to implement on high-end servers, which could be interesting, particularly if you think about the IoT, where many low-end nodes are connected to a high-end server. So you also want to have decent performance on those devices. And last but not least, which I think is the main advantage of permutation-based designs, is that it's very flexible. So with implementing permutation in a certain mode of operation, you get an authenticated encryption mode, an hash function, NPRF, and MAC, which makes it very flexible and also very nice to implement, because instead of implementing several different cryptographic schemes on your constrained device, you can now just pick one to address most of your use cases. This was my last slide. Thank you for your attention, and I'm open to questions.
Hello, thank you for the presentation. What is the state of like hardware implementations of the ASCON? Are there already actors saying we will implement this right now, we are doing this right now? Is this being industrialized? Do we still have to wait some time to know what's going to be done in the lightweight department?
So there are a lot of hardware implementations for ASCON, which are open source by the academic community, which are used for this benchmarking, also targeting for different trade-offs, not only for high performance, but low area, as well as channel protection. But for industry, we are still waiting for NIST to finalize the standard. So we, the ASCON team, are now working with NIST on drafting the standard. It will hopefully be public soon for comments. But as usual, NIST is always very busy, and this could take some time. We see it now in the post-quantum competition. We've seen it in the past for SHA-3. But I think we are close, and I hope that at least that the draft will be available still this year.
Thank you for the presentation. I may have overlooked the explanation, but could you explain the difference between PRF construction and the Mach constructions?
There is no difference. So basically, you can build a Mach from a PRF.
Okay.
You just basically truncate your output. So for a Mach, you basically take the PRF and you fix the output to 128 bits.
Okay.
But of course, due to the state size of ASCON, if you build a PRF, the security level of the PRF is limited by the key size and the size of the permutation.
Okay, thank you.
Hi. What's the advantage of AES over ASCON, like aside from all the standardization?
That's a good question. So ASCON is particular targeting for these constrained devices I've mentioned before, because it's efficient to implement. It's even efficiently protect against channel attacks, which is not so surprising considering that AES was designed before channel attacks were really known. So we had some advantage there. And if you do a new design, you can always tailor for the current platforms you have in mind, so you get this better performance. But I think if you look at high-end servers, we have an AES instruction in place. ASCON cannot compete with this performance. We're getting very good performance in software as well. But if you have a dedicated hardware support, like you have the AES instruction on your laptop, on your desktop PC, on your server, we cannot compete with that. And then again, ASCON has a security level of 128 bits, which is targeting for these low-end devices and these constrained devices. If you're thinking about high security applications like military use cases, you should still use AES with a 256-bit key. There are ideas how to do a larger key in ASCON as well, to achieve higher multi-user security, which I have not mentioned here, which might also be considered by NIST. We don't know yet, but that's more targeting for multi-user security, again, in this communication setting where you have session keys.
But with like dedicated hardware, dedicated instructions, is there reason to think AES would still be more performant?
I think if you do a dedicated hardware instruction, you probably will get the same security, the same performance. But again, key size is limited, text size is 128 bits.
Thanks.
Okay, then thank you.
Good morning, everyone. So today I'm going to talk about interactive Oracle arguments, which is a kind of protocol that I will define in this presentation. This was motivated by a question about the succinct verification of quantum computation. So this was our original question. So the original question was that if you have a big quantum server one day, so maybe 100 years from now, we'll have scalable enough quantum computer to do hopefully useful tasks also. And then you want to ask this quantum computer using your classical device. Let's say you're on your iPad. You don't have any quantum capabilities, and you want to ask the quantum computer a question. And the setting is that first, on the weekend, you set up with the quantum computer, you share some keys. This setup phase is not succinct, so this has communication that is polynomial in the amount of tasks that you want to do. But then when you go start the work week, then from your iPad, you can ask the quantum computer several questions using sublinear communication. So the whole issue we're doing here is that you're not trusting the quantum server. So you're assuming that, for example, you're the government of one country, and then you don't have quantum computer, but the opposing country has a quantum computer, and you want to send the tasks there, but you don't trust them. So we usually worry about two things: privacy and verification. In this presentation, we're going to worry about verification. There are other papers that deal with privacy, but today we're going to deal with verification. So I'm going to give you a 2-minute or 1-minute quantum computing primer. It's probably going to be very hasty, but classically, probably you hear this many times. Classically, you have the bit could be 0 or 1, which means like electricity or no electricity. In quantum, the one bit can be any combination in between these. So this picture that I have on the right side, you see you have two axes, like a blue one and a yellow one. So I want you to imagine that these are some sort of axes that you can define the quantum bit on. So information theoretically, you can define the qubit using two anti-commuting axes. If you know, like these are the Pauli X and Z, basically operators. So once you measure, it collapses. So you can measure in either the blue or yellow and observe. You'll get 0 or 1. But once you measure, the qubit collapses from this superposition thing. Now, this was the crash course on quantum computing. Now, remember, the motivating question is like, you get an untrusted server. The untrusted server is going to try to convince you that they did what you asked it to compute, right? So how can they do this? So basically, the idea is that you write down everything that you do. So the steps of the computation that you do on the quantum server, you just write it down on a sheet of paper. So once you have it written down, it looks like this. You have steps from 0 to t. So each step, you have the configurations of the quantum computer at a certain time step. So we're assuming that your computation is capital T time steps. Now, once you have written down everything, of course, the right-hand side are quantum states. You will put this in a big superposition over all the times, from time step 0, which is the input, to time step capital T, which is the output. So we call this the history state of the quantum computation. So once you have this big superposition, it has like mainly two registers: a clock register, which is little t, and this state register, psi t. So now you have written down everything, but you want to give it to the grader or verifier, who will verify that this is indeed a correct execution of the computation that we requested. So how can Alice, on the other side, using her iPad, verify all of this? So basically what she will do is that she will transform the quantum circuit into this set of criteria. So these are called Hamiltonians. So all of this business, if you're familiar with the MP completeness theorem for SAT, like this is all similar to the Cook-Levin theorem for MP completeness, which is basically, instead of Hamiltonians, you have a Boolean formula, and instead of the history state, you have the assignment to the variables of the Boolean formula. So basically, these set of criteria, they check mainly three things: that you have the input is indeed the input that you intended, the output is what you got from the quantum server, and you have a checker for the propagation from one time step to the other. And each quantum state, so now you have like honest servers which will actually perform the computation that you intended and give you a good history state. But you could have also cheating quantum servers that would try to give you bogus quantum states. So how can you like tell the good from the bad? So basically, when you measure this quantum state with respect to the, it will give you a number, which we call the energy. The lower the energy, the more honest the quantum state is. So you can think of the energy as a measure of the amount of violations in the quantum state. So now you have the quantum state, you have these Hamiltonians, which you can think of them as like a PCR test for the quantum state. if the quantum state is good, you usually get a negative value. You usually get low amount of violations. So you're on this, on the downside of this up and down arrows. And this is the theorem. It tells you that you can take any quantum circuit U and then you can transform it into a Hamiltonian such that if there is a state that makes the computation accepts, then there is a history state that has low energy with respect to the Hamiltonian. And the other way is if you have a circuit that doesn't have an accepting quantum state, then you can transform this into a Hamiltonian that has a history state, that for which all quantum states will have high energy. So, like I said, like if you make the gap between the honest and the bad, like if you try to amplify it, increase it, it becomes easier to verify. So it becomes easier to separate the good from the bad. So if you make it like really big, like for example, constant, in this case, you will basically need less samples to detect the violations. In fact, if you make it like so big that it's a constant, you will only need to check a constant number of qubits in a quantum state. So now this gives rise to the next topic, like now we went from the original question, which is verification of quantum computation, to this question about verifying quantum states against Hamiltonians. And then we're going to take that question and take it into another question. But now like scene one is over. Now scene two is, if you have this quantum proof, which is the history state, how can you verify it? So there is a dream concept in quantum computation called the quantum probabilistically checkable proofs theorem, which we don't have. We have an analogous theorem classically since the 90s. So the classical theorem tells you that any proof for an NP statement, you can transform it into a proof that can be checked by looking at a constant number of bits, 3 bits precisely. We don't have such thing for quantum computers, but hopefully we'll have one day. And this is actually one of the assumptions in this work. So once you have this nice object of a quantum PCP or a quantum probabilistically checkable proof, where your input is a quantum state and you can tell the good from the bad by looking only on a constant number of qubits. So once you have this, you can plug it into our framework, which we don't have as of today. Shame, because like the session is called constructions, but we don't have that. So this is the high level scheme. So once you have this nice object, you can go from computation to this nice object, and then you can use Merkle trees to get succinct communication, which was the goal of this project, is to get succinct communication for verification of quantum computation. So how does this work? So usually in probabilistically checkable proofs, you have a state that looks like this, and then you look at a constant number of qubits. There is some work that we do in the paper. For the sake of time, I didn't include here, but you can take this quantum. So here the verifier is a quantum verifier. It will take the quantum state 1 qubit at a time and perform the measurement against the Hamiltonian, check the energy, is it good or bad on the scale. So once you have this quantum verifier, there is a protocol due to Mahadev that can transform the quantum verifier into a classical verifier under the LWE assumption. So once you have this is like basically Merlin is sending the qubits 1 qubit at a time to Arthur or Alice, and then she is measuring the qubit, like she gets the qubits one at a time and she measures the one that she needs. Since we're working in the dream world, you don't have to measure everything. You only have to look at a constant number of qubits, but you must not tell Merlin which qubits you are looking at. So you will get the qubits, then you look at your verification sheet, like, do I need to measure this? If yes, measure it. If no, you just discard it, right? So if you have this, then under the LWE, you can make the verifier classical. I'm not including the proof, the details here, but this is using the Mahadev protocol. Once you do this step, your protocol will look like this. So you have a setup. Now we're in the classical realm. You have a classical verifier. You have the quantum server. First, you set up with the quantum server. This setup is independent of the task, basically sharing keys. You're setting up with the server, right? And then once you ask questions, you will get this interactive protocol, where you get first an Oracle message, and then a challenge, and then another Oracle message. And then you flip some randomness. Using this randomness, you will look at a constant number of locations in these two messages. So if you're familiar with PCPs, classically you don't need 2 rounds. It's just 1 round of the PCP, and then you look at the locations. Then since this was originally a quantum PCP, that's why we needed these 2 rounds. There are other papers that can get around this by other mechanisms, but this is the one that we investigate in this paper. So you have basically a starting point is a quantum PCP, you compile it into this kind of protocol. So we call this protocol the interactive Oracle argument. Now, how can you take this into the succinct world? So here, see that I'm only looking at a constant number of locations in the proof strings. So why should I send all of it? If I'm only going to look at a constant number of locations, why should I send the whole thing, right? So the idea is that if I have a stream of data, how can I commit to this stream of data succinctly? And the idea is used in a lot of places. Basically, we will use Merkle trees. So using a Merkle tree, you can use a hash function. You can use Florian's construction, maybe. And then you will hash everything up to the root. And then you can send the root. The root is basically of constant length. So you are committing to this whole stream of variable lengths using only a constant length amount of data. And then later, when you want to verify it, you only need to send data that is on the order of the depth of the Merkle tree. So now, there are 2 ways to analyze Merkle tree constructions. One of them uses uses concrete properties of hash functions, such as, for example, say, assume that you have a collision-resistant hash function family, or such and such. Like in quantum, the standard as of today is something called collapsing hash functions. We're not analyzing in this realm, so we're analyzing in the random Oracle model realm. So each one of these realms has its own pros and cons. The pro of using the concrete property is that you get more mathematically assuring analysis. But on the other hand, usually most of these assumptions are false. Usually in 30 years, 40 years, 100 years, people discover that this concrete realization is false, and then you try something else. On the other hand, if you use the random Oracle model, it's an idealized model that we know that we probably will not be able to realize in the real world, but it's a fake information theoretic security, because basically you're not assuming any concrete property of the hash function. Rather, you're assuming that the hash function behaves like a random function. So each one of these has its own pros and cons. We work in the second realm. However, we work in it where the adversary is allowed to be quantum. So not only that you can query the random oracle, but you are also allowed to query it in superposition. So you can prepare a superposition, send it to the quantum random oracle model, and then you get a response also in superposition. So here is the setting of what we have in the paper. So we define this object called the interactive Oracle argument, which is a generalization of interactive Oracle proofs. And then once you have this, you will use the Merkle trees to commit to the messages and get this onion root. So this onion root is basically the constant length that you will send as a commitment to the data. And then once you challenge, you will basically send the locations and the authentication passes. The size of the authentication passes should be proportional to the depth of the tree. So that's how you get, basically, since we're hoping for quantum PCPs that have constant query complexity, then you usually end up with logarithmic communication. So in this paper, we analyzed the post-quantum security of this protocol in the quantum random Oracle model. There are relevant works that did similar things. For example, in this paper, Kesa, Manur, and Spooner, they worked on analyzing if you have a sound PCP, then how you can use Merkle trees to get sound succinct arguments in the QROM. And later, they, actually in the same paper, they did another compilation where you can go from round-by-round sound interactive oracle proofs to sound succinct arguments. In this paper, we don't need the round-by-round soundness assumption, so we work with interactive oracle arguments without this special property called round-by-round soundness. And later they showed with Dandry under the LWE assumption that if you have a sound PCP, then under the LWE, you can get a sound succinct argument. However, in our analysis, we work in the quantum random oracle model, so it's a different realm. And also, our input is not a sound PCP. It's basically either you say it's a sound quantum PCP, or you say it's a two-round classical protocol after you classicalize it. So in conclusion, what we have is as input, we have the assumption of having quantum PCPs. So these are quantum proofs that can be checked by looking at a constant number of qubits. We assume the quantum hardness of LWE. So these are, like, to be honest, like shaky grounds. If I were to choose one of these to be true, I would go for the quantum PCP assumption. LWE, the world is betting on it, but who knows? Quantum random oracle model is kind of information theoretic security. So we have one complexity theoretic assumption and one computational assumption, basically. And then using all of this, you can get a quantum prover classical verifier argument for a quantum relation. And then you can compile it using Merkle trees to get succinct communication after a non-succinct setup independent of the input. So we do this for quantum computation, but we also have a general framework for compiling protocols, two-step protocols or more, into succinct protocols. We don't know of other usages besides this application in quantum computation, but the framework in itself is general enough so that, like, if you find any use case, we have two interactions or more, such that you only need to look at a constant number of bits in the interaction, or like a logarithmic number of bits in the interaction, then you can use this to compile it into a succinct argument. Yeah, that's basically it, and then we can take questions. I'm happy to elaborate also more on details after session if people have questions, but we can take questions now. Thank you for listening. Any questions? Are quantum computers real? Any kind of these questions? Okay. Yeah. Okay. If no questions, then I guess we can conclude. I'm happy to talk more offline also. Feel free to catch me. Great. Thank you.